This is video number 1 for section 5.4, Key Log Properties. In our last lesson, we introduced the idea of a logarithm. We wrote down something like this: log base b of x. The b is written lower, the x is written on the main line. And we said that in essence, this item is simply an exponent. What exponent? The exponent you would have to put on top of a base of b in order to result in x. Specifically, we said this means the power of b that results in x. Well, this section begins with a couple of very, very important properties related to logarithms. We're going to use these properties then to help us solve some equations. The first property is called the switching forms property, and it goes like this. Let me start by writing a statement in what's called log form. Log form refers to an equation that has a single log, a single base, a single result, and a single power. Log base b of x equals c. If you have an equation written like this, that's called log form. Well, the switching forms property says that anytime you have an equation written in log form, you can change it, if you so desire, into what is called exponential form. To determine the exponential form, you just need to think about our definition of a logarithm. Remember, a logarithm is a power. That means this c, this guy right here, is a power. What power? The power that you would put on b in order to result in x. Exponential form simply states that in the usual way. If I start with a base of b and I put on it a power of c, I will result in x. This statement is called exponential form. Anytime you have a statement in log form, if you desire, you can switch it to exponential form. And there's a double arrow here because it works both ways. If you have a statement in exponential form, you can, if you wish, switch it into log form. Now we'll see as we go through this lesson some of the advantages of doing this switch. Notice that each form has the same three pieces, just written in different places. Each form has the base, each form has the power, and each form has the result. You just need to learn where the correct pieces go. Here are a couple of simple examples down here. The directions say switch forms. Well, this first example obviously is written in exponential form. Exponential form is a base, a power, and a result. One base, one power, one result. To switch it to log form, I just need to write the corresponding logarithmic equation. To do that, I always start with the log. As a subscript, a little bit below, comes the base. The base in this problem is 3. Next to the log on the main line comes the result, the 9, and the logarithm itself is equal to the power. This statement also says 2 is the power you would have to put on top of 3 to get 9. This is the log form of this equation. In the second example, we're being asked to go the other way around. Now we're given a statement that is clearly in log form. One log, one base, one result, one power. I'm being asked to switch it into the exponential form. Well, all I have to do is identify the base. That would be the 4. Identify the power. The logarithm is equal to the power. You should say that to yourself a few times. The logarithm is equal to the power, so that 2 there is the power. And the result of using that power with that base is 16. 4 to the second power equals 16 would be the exponential form of our original statement. One thing that I keep in my head when I'm switching from log form to exponential form is I imagine this semicircular pathway because it works the same every time. Start with the little guy, raise it to the power, and that results in this final number. 4 to the 2 equals 16. Look how that works on this example too. Here's the pathway. 3 to the 2 equals 9. There it is. 3 to the 2 equals 9. Let's move on now to the second rule of logs, the power rule for logs. And this rule concerns something special that happens when you have a logarithm whose result itself is made up of a base and a power. So something that looks like log base b of x to the p. It turns out there's a special rule for dealing with this situation that's very important to us. To help you see where the rule comes from, let me do some math here. I'm going to set this thing equal to a. So a is essentially what I'm interested in learning about. Well, notice that as soon as I do that, I have created a statement that is in log form. One log, one base, one result, one power. I'm going to go ahead and switch that statement into exponential form. That would be b to the a equals x to the p. Remember that semicircular pathway? Here it is. B to the a equals x to the p. I would like to then solve this little equation that I've obtained for x. X is almost by itself. The only reason it isn't is it has this power with it. Well, that would be like a power equation. The way that I can get x by itself would just be to take each side to the reciprocal power, 1 over p. On the right side, p times 1 over p is just 1, so I end up with x to the 1, which is just x. On the left side, I can also use that rule about one base and two powers where I multiply the powers. So the base will stay the same. A times 1 over p is a over p. So I end up with b to the a over p equals x. Now this is interesting because this statement is a statement in exponential form. It's got a base, it's got a power, and it's got a result. I'm going to go ahead and take this and switch it into logarithmic form. So I write log. My base underneath is b. My result is x. And my power, remember the logarithm is equal to the power, is a over p. You can do that little semicircular pathway to check b to the a over p equals x, sure enough. Lastly, I would like to solve this statement now for a. Remember, a is what I was really interested in learning about. I can do that by simply multiplying both sides by p. And I end up with a on the right and p times log base b of x on the left. We'll take a look at the top line and the bottom line. The top line says this is equal to a. The bottom line says this is equal to a. Well, if they're both equal to a, then they are equal to each other. And that's what the power rule for logs says. Let's write that down. The power rule for logs simply says this. Log base b of x to the p is equal to p times log base b of x. In other words, if you have a logarithm and the result portion is a base and a power, that statement is equivalent to taking that power, moving it down to the front as a multiplier, and then multiplying by the remaining logarithm. This is going to turn out to be hugely important to us. Remember, we've been stuck for a while trying to figure out how are we going to get unknowns out of our exponent position that we're interested in working with. Logarithms are the secret, because with logarithms you have a way to move the exponents down to the main line. Well, there are a couple of sample problems here, a couple of examples to finish off. The directions in these problems simply say, here's an expression, you rewrite it using the power rule. In other words, according to the power rule, what is this the same thing as? Well, when I look at the first example, I see I have a logarithm, it's got a base, and inside here is a base and a power. It's an exact match for the left side of the rule. Well, according to the rule, what the rule says I can do is I can take that power, that 5, and I can bring it down front as a multiplier, leaving me with 5 times log base 2 of x. All I've done is I've rewritten this statement using the power rule of logs. Let's try it on the second example. The second example is also an exact match for the left side of the rule. There's no little base, but that just means it's base 10. The result portion is a base and a power. Well, according to the power rule, I can take that power and I can move it to the front as a multiplier. In other words, that z moves to the front, leaving me with log of 4. Again, understood base 10 there. The power rule of logs allows us to take exponents and get them down to the main line. Don't worry too much about the proof of the rule that we did in this section. The most important thing is that you learn what the rule says and that you understand how you can use it. In the next video, we will show how this property is what is going to help us to solve these exponential equations.